Okay, so let's assume that I assumed something wrongly. Maybe I was not organized, but let me sum up the main things we tried to do previously. Okay, so there is a structure of your problem. Your problem will be described by system, constraints, and a target. Okay, one of the functions that actually you want to implement is the function which gets you pre-image. To that function, you'll pass the description of the system, constraints, and a target. You'll generate the matrices M and L, and you'll form the polyhedron, and that gives you pre-image. Now, to get a one-step controllable set, you need to do one more step, which essentially means to project this to the state space. And these are few lines functions. Now, the thing that we actually reached was how to do one-step control set. Now, from the description in the slides, so shall I keep the slides with the lecture notes where there are expressions for the related things online, or? Okay, so if you look at the one-step control map, what we really see, we see that it's described by a set of linear inequalities. And all what you really need to do, you need to form this in a format that your toolbox likes it. Which means essentially you have to augment these two sets of inequalities, which essentially means below D you have to write a GB, that's your matrix P. On the right hand side you'll have E minus CX, and below that you'll have H minus GC minus GAX. The function to get one-step control set will have to have an additional input. The additional input will be the state of the system X. So you will have to pass system, constraints, target, and the state of the system. Okay, so once you pass this, you generate those two matrices, and you can just call that output. So can you, now, to be more specific, as one of your colleagues said, can you actually generate few lines MATLAB function, which takes in the system, constraints, target, state of the system, and it returns one-step control set. Can you code up that? All right. Why don't you take a time, code up that, and let me know when you have coded it up. And then we'll check some of these things. Okay.
How does U look like? Like, what is it out?
So, what you really know, you know that U is going to be a polyhedron, yeah? Because essentially, okay, so what I didn't say here, you'll say that U is, for example, you can make it polyhedron of matrices are P and R, yeah? Okay. Now, in general, if you have matrices P and R, you have its polytopic description. If you want to plot it and to use it as an object in MPT toolbox, you generate the polyhedron object, okay? But it's enough to have matrices P and R. This tells you that any U which works for you is going to be a set of controls which satisfy this set of inequalities. So therefore, once you have a P and R, which obviously depend on the X, and depend on the target, because target is described for G and H, you're done. Okay. So did you code up? I'll give you, I don't know, 5 minutes to code up, 10 minutes to code up this. I mean, it's 3 lines of the code. Things build up. I mean, if you do it this way, they do build up. And then actually when you do it recursively, that requires time. But I don't think that, I mean, it's you just pass the system, you pass the state, you multiply, generate matrices, form, and that's it. Now, the other question that matters for you, will it be true that these inequalities will be satisfied for any state? So what did we say in the slides? That actually this set is only meaningful for the set of states which belong to the one-step controllable set with respect to the target set. So only in the states in one-step controllable set, these inequalities will be possible to satisfy. Okay. So I'm giving you the time to code up this one. Now, if you want, you can take, for example, you can go back to the original example we had, or you can go to any of the examples you had. If you plot, for example, xk and xk minus 1, but perhaps it's simpler if you go to the original example. you've written down, and then you can see because they're going to be segments. Just okay. Okay. So you coded it up or?
No.
All right. So who's gonna let me know when you code it up? We have to have some communication, so I know you've done it.
I got
I beg your pardon?
control set view.
You did get it.
Yeah.
All right. So let me see what you got.
When you plot.
That's okay. So is that the first example we had?
No, it's the second, and it's this one.
Okay. No, that's fine.
Just use the next
Okay,
like this.
so you
Is that correct?
Yeah, that's a state. Okay, the state of the system will be given to you. This will be something that happens in the process, and then at each state you want to figure out what are the controls that work for you.
Yeah.
So that's fine. Now that means if you selected the states from that control set, you would guarantee to be to a previous set in the iteration. So I'm not so sure.
I just made one. Like.
No, that's fine. That's fine. Okay, that's good. That's good. So can I see your function for the control set? That's all. It's nothing else. Now, how would you actually? Okay. Target NS X state. Perfect. How would we do this? If you remember the iteration that we did n-step problem. So for the n-step problem, what was the fact that we used? We essentially just used the fact that xk plus 1 is a c of xk, yeah? And x0 is equal to xf. Which essentially means that you have called this one-step controllable set function n time. And you have just updated your target set. If you look at the code at the nc step function. Yep. Okay. Now, how can you reuse your function for one-step control set if you have a dynamic target set? What you would need to change? The only thing that you would need to change when you pass the code, when you pass arguments to your function, this g that you use in your function would have to be associated with the effective target set. So the very same function you generated, the control set, would work with a different target set, but you don't pass this g and h. Rather, at the kth step of iteration, you pass gk and hk. Yeah. So that's all what it means. You just give different argument to your function, and you have a function to construct the n-step controllable sets. So now, what is the problem actually you want really to solve? Okay, so let's suppose that you generate this sequence of controllable sets. And if I ask you to actually try to answer the question of the, let's say, minimum time control, so you want to solve the problem of controlling the system to a target set in a minimum time. Such a problem may appear quite relevant in several applications. In many applications, some of which are military applications, obviously. So the question arises, how can you work out that? Well, one of the things, if you do have a stored sets x0, x1, xn, okay? And if I give you a state x, you can say, okay, let me find an integer I such that x is in xi. Yeah? My state is in a specific controllable set xi. And actually, let me also find a minimal such I. Yeah? Smallest I. So let me write more clearly. Smallest I such that x is in xi. Now, if you find the smallest such I, what does that mean? That means that actually for this x, we have this inclusion, x element in xi. But this implies that there is a control u such that xu satisfy constraints y and system f of xu goes to the set xi minus 1. At least that, yeah? So if we come back to our polyhedral setting, so a relevant problem is transition from xk to xk minus 1. Yeah? This transition from xk to xk minus 1 means find the u. Okay, so you are given an x in xk, find the u such that what constraints do you need to satisfy? Cx plus du less or equal than e, and the other one is that actually you need to go to the xk minus 1, so it's going to be gk minus 1a plus gk minus 1b less or equal hk minus 1 minus gk minus 1c. This is x and this is u. Okay, but if you look at these things, if you move this cx to the other side, and if you move this part to the other side, minus gk minus 1 ax, this is nothing else than what you've just done for the one-step control map, yeah? With the convention that instead of g, you'll write the gk minus 1. So that means that essentially you have to pass the effective target set xk minus 1 to your function, yeah? So, now what you're going to tell me as you plot it, generally this describes the set of good controls, but what you really want to implement to your system, you want to implement a specific control. Yep. Now what does it mean to implement specific control? Well, because the control is not necessarily unique. You can choose controls. You have to determine a rule by which you want to choose a control. And what rules would be specific? What rules would be meaningful? For example, if you want to save energy, what would be the best rule? So minimum effort or minimum energy control. So one such a control can be constructed by minimizing two norms of the control subject to u in u of x. Okay, so let's find this specific control. Now, I'll assume that actually you have constructed this object because you have a function. Once you have this object, you can extract these matrices back, yeah? P and R, by just using P equals U dot A and R equals U dot B from the, okay. So now what you're given, let's call this PK. Okay, so you're passing it with K minus 1, let's call this PK minus 1. Okay, let's call it PK minus 1. So this is going to be U dot A in the MPTs, and RK minus 1 is going to be U dot B. This is how you retrieve the matrices. If you look at this minimization problem, what you're going to obtain, you're going to obtain minimize U transpose U subject to PK minus 1 U less or equal RK minus 1. Now this problem is nothing else than the quadratic programming. Did you use quadprog before? Quadprog function of the MATLAB. So therefore you can actually code up this using the quadprog. Okay? So find U using quadprog. Okay? Now, let's break the things in the following sense. You have a function which gets you one-step control set. This tells you what are the admissible controls in terms of inequalities. Let's say that we have a rule to figure out the minimum control effort. To figure out that control, given the admissible controls, we'll choose the one which has a minimum 2 norm. Okay? So we can equally minimize the square of the control. Now, to find this control, you do this in the quadprog. So let's call this function, instead of one-step control, let's call it, now, for dynamic target set, we understand that we can use just essentially the very same function, one-step control set, but we change the target set. We put the target set to be xk minus 1. Is that clear? So you can reuse the same function. Now, let's call the function one-step control. One-step minimum effort control.
Sorry?
Sure.
It doesn't show on the film when you write.
Okay, so if it doesn't show, I'll have to erase something. What can I erase?
First part?
Is it okay if I erase this part?
Okay. On this part.
Yeah, the one, what you wrote first.
Okay. All right. Okay. So, you're saying this one?
Yeah.
All right. One step controllable set, can that go? Okay. And step is gone. Okay. All right, so let's say one step minimum effort control or minimum energy. Okay, so what we said, so you have to be given an x, and you have to know that this x belongs to the xk minus to the xk. So you have to know that actually you can transition to xk minus 1. Okay, so what you do, first step, you construct uk minus 1 of x. This means you use your one-step control function with the target set xk minus 1. Okay? So, use one-step control function with xk minus 1 as the target set. Okay? This is explanation, so it's written in a... So I think my words are clear, yeah? So you use this function with the xk minus 1 as a target set. Now, construct pk minus 1 as a uk. Of course, when you get back from your... Okay, so you construct uk minus 1 of x, but your code is going to return you the set uk minus 1. You'll get just polyhedron for that specific. It's not a function, yeah? So you can say this is u, let's call that u dot a, and you construct rk minus 1 to be u dot b. Okay, so this gives you description in terms of inequalities, and then find u by solving quadratic programming quadratic program u transpose u. Okay, minimize with respect to u transpose u such that pk minus 1 u less or equal rk minus 1. Okay, that's all. And return u, which is the optimizer. Which is the optimizer. Okay. So this is a bit more elaborate in terms of programming, but again, it's a few lines. It's not elaborate because you use everything in the background. So for a given x, you construct the u, you construct the matrices, you form the QP, and you get it back. So it's again 4 lines of code. I'll give you 10 minutes to code it up. Sure.
This x.
Now you have to look up quad prog syntax. It will require you to pass in the Hessian, gradient, and the free term. So the Hessian would be identity matrix because you're minimizing u transpose u. The gradient is 0. There is no free term. It's also 0. If you want, you can add some Hessian to have a different weights, but it's okay if you do it with 1. And this matrix is okay. So if it's simpler, we can call this matrices P and R. You don't have to worry about indices as long as you know, as long as you keep a track of a time when you're doing things. Okay. So say it.
X is a point or a range?
Which one?
This when you compute R. E minus Cx. So X is xk.
So X will be given to you. Now, what's going to change? Your G will be gk minus 1 and hk minus 1. So this will be, if you look at the nth step, we have generated essentially effective target set. So we were using these matrices. So you have to use effective target set, not the final target set. So your target set propagates through the dynamics. Typically, you start from a target set xf. This then propagates, and this is your x0. This then propagates, so you get x1. It propagates further through dynamics. You get x2. Propagates further, x3 and so on forth, and then actually it goes over my writing. So it's not, it doesn't propagate anymore. It hits the constraints. So the point is, so these are propagated, yeah. So one step target for x1 is xf. One step target from x2 is x1. One step target from x3 is x2. So one step target from xk is xk minus 1. So that's the effective step you work with when you do one step controllability problem. Okay? Go on. Sure.
Alright, I haven't finished the first bit of constructing U, I think.
Okay. So you're constructing U.
Yes, I'm trying to.
Actually, your colleague has done construction of U.
Yes.
Okay.
The rest of us haven't.
Okay. So take your time. Is there anything I can help with that? Okay. Now, so what you need to do this, okay? You just pass to your function system constraints and a target. Now, target as a variable can be different at different times you call this function. At the moment, what matters, we know that we have G and H in a target. You form the matrix P by doing D and G times B, and you form matrix R by doing E minus CX, H minus... Now, you need... X is a state of the system. X is a state you want to control. So that's going to be input to your function.
Yeah. So what should I...
Well, you pick an input from a controllable set. So that's actually... We are building it from bottom up. Okay, so we need afterwards to figure out what states we can control. At the moment, you can think of that as an arbitrary state. But not for all states is guaranteed that you can find the control. Only for states which satisfy certain controllability conditions, being in controllable sets, you can actually find that these sets are non-empty. Okay, so once you have this tool, that would give you that, and then actually using this, well, really those few descriptive steps, you can code up a small function which gives you such a U of x, minimum effort U, and then we nearly have a control algorithm which uses this. And that would be the final step. But I think I'll leave you 5-6 minutes to code it up. If anybody wants to ask me something, I'm quite happy to drop by and help.
So, since we're trying to minimize U, and I have like this sets outwards, right? That means like if we are like really close outside of the first set, then it will just move to the edge.
Well, so essentially what it says, if you look at, okay, so perhaps this is the best explanation, yeah? Now, you have a function which gives you back description of this object, yeah? And then actually you're picking a specific control out of that set. Now, this control doesn't mean it is best in all senses, but it's a best in a sense that actually you want a minimum norm. So if you wanted a minimum norm control in this specific example, as a function, when you're at -4, it has to be that point. It would lie along this line. When you're here, it would be 0. It's a minimum effort, don't do anything. And when you're here, it would be there. Yeah? So as a function, control, minimum effort control would be that function. Piecewise affine and as a function, okay. It doesn't mean it's the best function. I could have equally told you, maybe, what you want, instead of minimizing this, maybe you want to minimize norm of the state at the next point in time. Yeah? So there are many rules you can come up with. I just asked you what if the rule was to have actually minimum effort control. And then we said that's the rule. So different rules give rise to different control functions.
For this example, say that if the initial state is 2.1.
Okay, so if the initial state is 2.1, how would we control it? Okay, so you start from x0. It's not in x0 because target is 0. Okay, so the first controllable set is -1 and 1. Is it in between -1 and 1? It's not. So it's not in the first controllable set. The second controllable set is -2, 2. Is it in second controllable set? No, it's not. We cannot control it in 2 steps. Is it in third controllable set? Find the smallest I. X in xi. So it is in the third controllable set. So 2.1 is between -3 and 3. Okay? Once we know that it's in third, we know that actually it can transition in one step to the x2. So what you really do, you find the control which moves you to the x2. Your state was 2.1. Okay? So x plus was x plus u, yeah? So 2.1 plus u. So minimum effort control would be minus 0.1. So it would push you just to 2. Now you have a new state, you can repeat the algorithm, but now you don't have to, you have to run only up to a 2. So you check whether it's in 0, 1, and 2. So you say it's not in 0, it's not in 1, it's in 2. Because it's in 2, you know it's 2, I want to go to 1, now I have to push the control which is minus 1. So I push it to 1. In the next iteration I check, is it in 0 or in 1? It's in 1. At 1 I have to push control minus 1. I do minus 1, I make it in 0. So in 3 steps I make it 0. And that problem is called time optimal control to the origin. But that's the final step. So I was thinking that this was gradually building one by one was more natural way to do it. And that's why I said if you bear with me, everything will come together, even though it might look a bit disorientated, but eventually it does come together. Okay. So
Out of charge.
okay. So did you manage to code it up? I mean, have you made a progress with coding it up? Okay. Okay. So now, I think at this stage you have all blocks to build the control strategy. You have a ways of building controllable sets, you have a ways of selecting the control at a given state X, and all what you would need to do now, we would need to put together control algorithm. Now, if you go back, for example, why don't you go back to this example and check what I was plotting that it's fine, with using your U at different points and plotting it. Okay, so you managed to code it up, or?
I'd save it at my home space.
Okay.
It takes 5 minutes to initialize when I start up MATLAB, so...
Okay. Well, all right. So I'll come back in 5 minutes. Okay, so you're looking at the instructions. So am I expecting too much? Still expecting too much?
Something like this, or?
Let me see. Okay. So can you plot this? Oh, let me see. What do you get out of it? So you get one-step control. You need a state X. That's fine. You need a quad prog. That's fine. UA, UB. I think that's absolutely fine. Okay. So that would be your U of X. And now what you can do, for example, you can take. Now what you need to know when you construct the one-step control map.
Yeah.
Here you're passing the target. But actually when you do this in n-step manner, you do want to take update of your target set. So when you're making transition between k to k minus 1, k and k minus 1, your effective target set becomes xk minus 1. Okay, so in that case, you call the same function, but your target is not xf, it's xk minus 1. Okay. So these controllability sets are the means of propagating your constraints over long horizon to one-step problem. So whether you solve the long horizon problem with many constraints, so you solve one-step control problem, the constraints are hidden in the shape of your controllability set. And what I will do for you is later on when I look up at this for today, I'll dig up these examples when you get these nice shapes, because this depends on the target set and everything. So I'll set up one code for you so you can have a feeling. But ultimately, I do want you to kind of be able to implement a control algorithm based on this. So I'll wait until you finish this one-step control map function, and then actually we'll see how to put all this together. How to get kind of, let's say, minimum time control to controllability set. Okay. Okay. Okay, so now so have you managed to make progress with?
Yeah.
You have.
Progress.
You're going.
So once I've generated U from this,
Okay, that's a U as a big set, yeah. Okay,
yes.
that's a big U. Okay.
yes, then I just set.
So then essentially, okay, so you have big U, you can get these matrices, and then you can solve the quadratic programming U transpose U, P U less or equal than R. To solve this quadratic programming, you use a function quadprog.
So the U, the P there is the same as the P construct.
That's correct.
So
But this P and R will change in the control process because your effective target set will change, which means your G and H matrices will be changing. Okay, this will be changing. So therefore, at different states, you'll have different. So first, at different states, you'll have different set of admissible controls. So that will restrict your selection. So as your colleague was asking, if you look at the minimum effort, when you're at this point, you can select only that point for a U. So there is nothing to worry about. It's that selection. If you want to minimize U, you tend to push U towards 0. Yeah. So effectively, you will be pushing U on the boundary of this. Once you reach this point, there is a switch because at this point, U equals 0 becomes feasible for your constraints. So you can stay at U equals 0 at these points. And when you're here, you hit this boundary, so you stay on that boundary. So as a function, minimum effort control will be essentially piecewise affine. The consequence of this is essentially structural dissolution of parametric quadratic programming, but it's not a topic of this. This is concluded just by logic. If you want a minimum effort, you push closest to the 0, and what's the closest to the 0 is what is on the boundary in this case, until 0 becomes feasible.
But why do we construct large U and then immediately?
Because large U is a set of all controls. And if you want to physically implement the control, you cannot implement the whole set of controls to the system. Control is typically one value, one point in this set. So it's not physically possible to realize the whole set of the controls. Yep. Okay. So is it at least a bit clearer now? Does it become connected together? No. Okay. Is it still too Is it still too fast? What I expect you to code up?
It's better, almost.
Okay. All right. So.
And where do I get the X from?
X is a state. X is a state of the system.
Yeah.
So at the beginning of the process, you'll be given X0.
Yeah. Okay. So this is.
And then once you have X0, you choose a control U0, you implement.
Okay.
Now,
so we don't
what-
have any X0 given yet. This will get
that will be for a control process. You can choose a random state and it should work for that state. For the time being, pretend that X is given. And it will be given as an input. You can take an input. If it's feasible, the set will be non-empty. If it's not feasible, it will give you an empty set. But that's fine. All what it says is say it's not in controllable set. That's all what it says. So in other words, I mean, if you have a, well, this perhaps imprecise, but a simple example. If you have a 2,000 euros in your bank account, it's very unlikely you can buy the newest Mercedes-Benz. If you have a 2 million, then it's very likely you can buy it. So it means it's in your controllability set. I'm not trying to be politically incorrect or anything, but what I'm trying to say, given certain geometry of a problem, there are only certain things that are possible. So once you have a constraint on the system and a dynamics, this specifies what can be done. So for a given state, if it's in a certain controllability set, there will be control. However, if it's not in any of the controllability sets, there is nothing you can do. It's simply just not consistent with the constraints. It's not possible to generate a control process which will allow you to keep system within the constraints and dynamically consistent. Okay, so tell me, how far did you manage to get?
I don't know if it works, so it's a bit hard to say.
Okay, but can I look at the code?
Well, I spent half the hour installing MATLAB again.
Okay,
because I
okay,
had the old
okay.
version.
All right. So let me see. I think that, let me see. You're doing it in a loop. Control map, that's fine. Can I see your function control map?
Yeah.
So PNH, that's fine. Can
Yeah.
you go back to the main function?
That one?
No, I don't know why do you have a loop.
Maybe I misunderstood what we were.
No, you shouldn't have a loop. There is no reason for a loop. It's just essentially one-step thing. You don't have a loop for a small u. It's just a quadratic program for that. Okay?
Does it make a problem?
Okay, U set UA, UB, let me see. The number of columns in A must be the same. Okay, can we see what's the number of columns in
A is 6 times 1.
what is B?
B is 6 times 1.
Can you give me your H?
It is
So that's a problem because U is one-dimensional. How did you get H to be that big?
etc. Okay, should be not.
Well, U is one-dimensional, yeah?
Okay.
So H should be dimension of B, yeah? Size of B1, but I still don't know how did. All right, so you have a size of A. It should be system of A. Because your A is number of constraints. If you just change A to size A, I think that should work. Sys A. Okay. All right. So. Okay. So can I erase these things now?
Okay. No, it's okay.
Can I erase this? We have somebody whose code will very likely go on the slide so far. So let's see. Okay, what did you get?
0.1. Minus 0.1.
Minus 0.1 was for?
The same example I told you.
You're getting these kind of things.
Yeah. From minus 3.1 I got.
That's good. That's good. Okay. We need a final piece of a puzzle. These are all building blocks. You need to put things together. Okay. And I didn't tell you what. Look, I'm asking you to paint the picture, and I didn't tell you what the picture is. So I understand it's a bit unfair, but you have to get these notions and understand they are just blocks you can use to solve many problems. That's what I want you to do. Okay. So let's now solve the following problem, okay? So let's solve the problem. Let's solve the problem. Minimum time to target set control problem, okay? So let's solve the problem in which we want to go to a target set in a minimum time. Obviously, this problem has a lot of applications in racing, military, etc., etc. Now, you are given the system, you have a tool to pre-compute, so say you fix an n, arbitrarily large n, and you pre-compute controllability sets, x0, x1, xn minus 1, xn, yeah? You have this pre-computed offline. You don't have to do this online. Now, what would you do online? So, first step you would do, find smallest I such that x in xi. So this is for a given x, yeah? For a given x. And x will be a state of the system in the process you control, okay? For a given x, find an I such that x. Okay. Second step, construct. How did we call this control? One step minimum control effort. One step minimum effort control. Okay. Construct, implement, and let's call that U star, yeah? U star of x. This will be U star of x. Okay. Get a new x. Okay, and then what you really do, you just iterate, yeah? This is your control algorithm. Yeah? Now, there are a few things that you want to observe. This new x, when you don't have uncertainty, so if this was, so you're given x, say xk, your xk plus 1 is going to be axk plus b u star of xk plus c. If c is given, whatever. So what you actually predict with your system, because there is no certainty, is going to be what you're going to see. Yeah? Once you have the xk plus 1, finding the smallest I, okay, can be restricted to I optimal of xk minus 1, yeah? When at xk plus 1. Okay? So why so? Because if we know that at xk we can do it in I steps, at the state xk plus 1 we are guaranteed to go to the I minus 1, yeah? So therefore the search without uncertainty should allow us to actually find the control in this x for the I minus 1 time, yeah? So how would you implement this? So in the offline stage, you would construct this control n-step controllable tube or n-step controllable sets. In the online stage, you would have to have a function which for a given state of the system figures out what's the smallest I such that x in xi. For this, actually, you can check membership test in the MPT. I think actually you have a question is in xi x. You specify the set. We'll look it up together. Now, once you figure out that index, so essentially that means you go, is it in x0, is it in x1, and so on and so forth. The moment you find in which one it is, you stop. Now, if it's not in any of these sets, you just say the current state is outside of the controllable sets which are pre-computed, which means you cannot generate controls for such states. In that case, you can go back, generate more controllable sets, but presumably when you generate these controllable sets, you cover the region of interest, or the set of states that you actually wish to control, or you expect to control. So, once you do that, you have figured that one, and then you implement computation of one-step minimum control effort. Now, here important thing is with target set xi minus 1 as the effective target set, yeah? Okay, that means when you construct this map U, these matrices will be gk minus 1 and hk minus 1, yeah? Okay? You implement this control, which means you generate xk plus 1, and you just loop this. Okay? Is this clear how to code up? How to generate a function for this control algorithm? Okay, I think actually it's a fair amount of details. You should be able to put it together very quickly.
Very quickly.
No, I mean very quickly when I say, I mean by the time we finish today. Any questions? Go on.
Find smallest I.
Uh-huh.
What do you mean? Like,
So you start from 0. So you ask yourself,
okay, so
is x in x0? If yes, x is in target. There is no need to do any control. Okay? Then x is not in x0. Is x in x1? Is x in x2? Is x in x3? Yeah? So if you just go to the MPT and check how to check membership, how to check if the point is inside of the set. Now, on the other hand, what you know that your xk has a description gkx less or equal than hk, yeah? Whether x belongs to xk, this is equivalent to check whether gk x less or equal than hk. So you can check it evaluating number of inequalities. But I'm pretty sure there is a built-in function in MPT. So if you do help polyhedron, it will list you what are built-in functions and methods. So I think you should, or in, okay, I'll look it up myself. So any other questions on this control strategy? Okay, so graphically, what we have done effectively, you have x naught as a xf, then you have a x1, you have x2, they might be overlapping or not, then you have x3, then you have xn minus 1, and then you have xn, yeah? So say you figure out your state is in x3 by doing this. That means there is a control which when you compute you're guaranteed to go to the x2. At the next time of the iteration, you know that you're in x2. If you're in x2, there is a control which will drive you to the x1. Once you're in x1, there is a control which will drive you in the target set x0. Okay? And don't expect you get everything right on the first coding. I mean, when I was coding, when I was a PhD student, I would be very happy if it works after an hour of coding. There is always something you... Okay, so shall we look up how to check if the point is inside of polyhedron in MPT? I mean, I was thinking that actually that would be in demo. If you have any questions, ask me. I won't be giving you anything else for today. That would be all what I want you to put together. And that would be the first control algorithm you have for the constraint control. You would be able to solve minimum time control problems. Polyhedron. Is inside. I think there is a containment. Okay, so x of, I don't know what I've been computing. So this is if we take 0 minus 8, it's not inside, okay. So is inside.
Okay, we'll just return P. Yeah, P is the same as U dot
So this is so minus 8. Okay, so actually you have the way you do it is okay. So the way to check if the point is inside of the set, you have a set and then you have a method is inside and you specify what's the point. Okay? So you can have this in a loop for I equals, now you have to count, you have to keep in mind that when we start indexing from 1. So what is x of 1? It's actually x0. That's a target set, yeah? So you have to keep in mind that counter is shifted by 1. Yeah? So what you would do, you run from 1 to n plus 1, and you check to n actually how many controllable sets you've generated, and you check, so you go x of I dot is inside x, which is given, and you figure out the minimal one. When it is, you break the loop. So actually I think you can actually do it in a while loop rather than for, but I'll leave that to you. So once you figure out that one, you construct the one-step map, you construct one-step minimum effort control, you implement to the system, and you repeat. You iterate. So that will be done. So you will need a loop which will represent evolution of the system, which will be outer loop, and then you will have an inner loop in which actually you are figuring out control algorithm. Yep. You can do a number of simulations, can be, I don't know, specify anything you like. Or you can have just 10 number of steps you go to a target set, and you can terminate. You can give just information that you have reached target set. Okay.
Yeah, but well, yeah, that's the one step. But one
So any progress?
more steps. You are doing two steps.
Managed to do anything? Okay. All right. So I mean, look, it's a first day, so maybe I kind of tried to ask you to do too much, but I think actually for the first day we have put together one of the control methods, and if it's any, I mean, this is a control methodology in its own, so it's time optimal control, and you have a solution for it in a discrete time setting. So what you need a set. You need a set, and then you do dot in. So the set has to be polyhedron, and you do is inside, and you specify point. Actually, let us check. Actually, I've just taken the point which is 0 minus 8, which is clearly outside, but let's take 0 0, which should be inside. Okay, 0 0 is inside. So you'll get a logical answer 0 or 1. So if the point is inside of the set, you get 1. If it's outside of the set, you get 0. Or if it's not inside of the set, you get 0. Okay. So just ask. Don't hesitate. Go on.
No, it's just that I'm thinking while I was generating the question, and then I have to start to think.
Okay. Well, I can't answer question I can't hear. I struggle with the questions I hear, let alone questions I don't hear.
But when you go from 1 to n and search through x, find
is the point inside of the set.
yes.
Okay.
Should you try to, since x of 1 is the largest set?
Well, I mean, we don't know.
At first
So far, we don't know what's the largest set.
Okay, so you
That
start
may
with
so.
1 and search.
Yeah, that's correct. So
Then
we
you take
don't.
the first one you find.
We don't know anything. You take the first one you find, because the problem is minimum time. So you're finding the minimal controllable set in which minimal of n step or k step controllable sets in which the state belongs. Once you have found specific set, what you really know, you know that the state that you want to control can be controlled to the xk minus 1. Okay, so find the control which does that. Once you found the control that, because there are no uncertainty, there is no mismatch, there is nothing, we know that at the next point in time when you do search, the state will be at most in xk minus 1. It might be, if it's pushed far enough, it might be in some of the smaller ones. So you want to check between 0 and k minus 1. Once you find a new index, you again do the same trick and you do again. So essentially what I'm trying to do, you can shrink the search once you have found the initial one, but only without uncertainty. When there is uncertainty present, that cannot be done. So a good idea is to do a search without restriction. So if you add a small perturbation to the system, you can still kind of find the control. But because we are doing deterministic problem, there is nothing about uncertainty, you can actually restrict the search to the smaller subset of indices. Okay. So now I think 1544, and I did. So do you have any other questions on this? Let's use this time just to wrap up on this construction. So if you have any questions, just go.
Okay, so control U, which was mainly.
Okay, that's one of possible controls. There are many other rules. Let's.
This step is how doing like one step at a time and not looking into the future. It becomes non-optimal, right?
Well, so to answer that question, there are a few things. Okay, if you wanted to do for the future times, you would have to make predictions, but we are about to come to that. So that's kind of ultimately what we'll be doing. At the moment, you're just doing one step. Okay. No, actually, you can find it in an optimal manner. But that would be it's not this kind of argument. So this kind of what this tells you, there are several messages of these lectures this morning in this construction. It tells you that actually, because of the constraints, it's only subsets of the state space that you can control. When you do these controls, you have to be very selective with the controls you choose to achieve the control. That's a control map, which is described by inequalities. You're getting a feeling of the kind of control map that I was specifying, and then actually how to do that in an iterative manner. If you increase the number of controllable sets, then you iterate on it using dynamic programming, and then actually you're breaking the k-step control problem. So n-step control problem is broken to n one-step control problems. Okay, so of course you can, because everything is deterministic. At a given state, you can solve p one-step problems. Nothing stops you from that. But the whole point of this is to do in a closed-loop fashion, meaning that actually when you push the system, if some discrepancy happens, you still look for a control rather than actually fixing control. So you re-evaluate the state given on the new U. But actually uncertainty and what happens when you have uncertainty is the topic of tomorrow's talk. So tomorrow we'll look what's the effect of uncertainty on these things. Okay, how to handle uncertainty in this framework. Okay, so any other questions on these constructions? Now, can I ask you one thing? Intuitively speaking, you kind of encounter term stability. Do you know what stability is about, or? Okay, so do you think, for example, this minimum effort control would lead to a stable behavior?
Yes. For this system? Since the constraint is that the new step has to be closer.
Because the system is linear, with a suitable choice of terminal constraint set, it will lead to stabilizing behavior. But you have to keep in mind that k-step control, it's not time invariant control, it's time varying control, yeah? Because at every point in time, your map, the one-step map, works on an effective target set, xk minus 1. If you're in xk, your effective target is xk minus 1, which means that actually the map you compute to transition from xk to xk minus 1 is not the same as the one you would compute to transition from xk minus 1 to xk minus 2. They are different because the matrices G and H change in that expression. Yep. So that's why actually when you generate these functions, they should have a target, and then actually when you call the function with a different target set. The constraints and the system description don't change, but the target set becomes dynamic, so to speak. Okay?
Then how does that affect the stability?
Well, it's first, I mean, it's a time. The control law is time varying, so it's a kind of you need to look at the stability for time varying systems. That's the first thing to begin with, and secondly, actually, because this only pushes you to a target set. It doesn't tell you what happens in a target set. So if the behavior is not stable inside of the target set, you can't talk really. That's why I initially said under suitable conditions on a target set, things might behave stable. And we'll touch upon all of this. Everything comes kind of one block at a time. Okay. Any other questions on putting these things together? All right, so can you put it, I mean, did you manage to put all these things together? Okay. Right, you have, but is it clear what you would need to program up? Okay, so I think essentially as an objective, what you need to program up is clear. I mean, only clear thing would be that I code it up and give you code to play with, but then it's not hands-on experience. Also, you're getting used to new toolbox. I mean, I don't know all functions of this toolbox. I need to look it up at the kind of help function. But okay. So I think actually we'll stay another 5 minutes and we'll call it a day, because we kind of had 2 sessions instead of 3 regular sessions. I would like you to use these 5 minutes for any questions in regards to the lectures or in regards to the code. Do you have any questions whatsoever?
Which is the new Imensus functions that you just made by yourself. You're able to control into target sets. Okay. This is just the same question for what is the
Did I make a mistake in description or? So you have a file. It's all right. I'm here to help. Just ask me questions without hesitation. I is an index. It's an integer. So I is a time which you would, yeah. So I is a time which you would need to go to a target set, yeah. If I is 0, it means you're already in a target set, because x0 is a target set xf, yeah. If you find that I is a 3, that means your state is in a 3-step controllability set, yeah? So it means it can be controlled to a target set in 3 steps. And to do that, you would go from x3 to x2, then from x2 to x1, and then from x1 to x0. You would do that because this is a closed loop strategy we are doing. Yeah? Essentially, it tells you for a given state, I know what my target set is, I'm solving that problem. And the control we selected, this minimum effort control, is one possible control. There are many other control rules you can come up with. You can minimize the norm of the state at the next point in time. You can do all sorts of things.
But now we're minimizing the time. So what do we want to return from this function? Yeah.
So in what do you want to return? What you would like to return from this function is what do you usually return when you control the system? You return the inputs, you return the controls, states. Yeah? So this is something you may like to plot. I didn't say that, but I assume that would be something which would be easier. Okay.
For the next iteration.
Big pardon?
For the next iteration. And then you compute for...
So you iterate on this, yeah? So that's a base block. So you will have that in a loop and you do these kind of things. Okay. So if you don't have any other questions, I think what I would do, I would later on when I get to my hotel, I'll send you the link for the literature. If you don't mind, what I'm going to ask you, I'm going to give you like 2-3 days until we kind of catch up on coding up these pseudo things. And at that point in time, I'll ask you to send me your representative code for one of the problems. And I want to put this on a set of slides so you can actually exchange your codes. For this exercise, however, I did promise you to look up some of these more exciting sets and shapes. I'll try this evening, unless actually I crash completely when I get back to get rest. I'll try to put up a script with the example, which would actually, well, maybe I'll code up things myself so you have my code to compare to your code. But I really want you to have this hands-on experience. I really want you to code up things and see things yourself. I think that's much more useful. Even if you get errors initially, we can compare the results. As you actually evaluate the sets, all of you, you can compare the results and try to figure out what's wrong, what's right. Otherwise, if I give you the code, what you would be doing is essentially would be just running someone else's code. So I don't see any benefit from in terms of learning.
Makes it easier to understand what you're doing.
Okay, it's the first time you're meeting with something, so it's a bit convoluted. It's going to become much easier as we go on. I'm pretty sure. But I'll set up definitely data which should give you good illustration. That will definitely do. Now, final call for the questions. Do you have any questions on the parts we looked at today or on the code you tried to do? So to sum it up, you had a code for the pre-image. That's one function. Then you had a code for one-step controllable set. Then you had a code for the k-step controllable set, which was actually iterative call of this one-step map. Then you had a call for one-step control map. Then we figured out that we can use that one-step control map to kind of use dynamic target set because you just changed these matrices. And then we had a specific control selection, which was the minimum effort control. For a given state, in a given controllable set, we were able to do. Now, important thing to note here is when you figure out the text is in xk, which actually you do in a higher level algorithm, which is exactly finding this index I, then actually you construct the one-step map yk minus 1 of x, which means the matrices are gk minus 1 and hk minus 1. So your effective target set is xk minus 1. Keep that in mind. You're transitioning from xk to xk minus 1. Effective target is xk minus 1. Right. This strategy, even though system is deterministic, is a closed loop strategy because you're doing it sequentially. Given a state, you're figuring out what controllable set you are in and you are evaluating associated control map or specific selection. This is a control function which is minimum norm here. Okay. So that's all for today. And tomorrow we'll see what to do in terms of positive invariance. And then we'll do what is the effect of the uncertainty. Intuitively speaking, when you add uncertainty, do you think that equivalence between open loop and closed loop will hold? No, it's not going to hold, of course. I mean, if you remember that example I mentioned about the car and crossing the road, if you know that in that model, or the road you're crossing, if you know that there are no cars on the road, then it doesn't matter if you do open loop or closed loop. You can do whatever you like. But if there is a frequent traffic, then of course it matters a lot if you look each time you make a step or you don't look. Especially if you're, for example, in Italy or France, where people don't respect regulations that much. So in some countries they respect the laws more than in the others, so you're kind of safer. But in either case, you don't want to bet your life on the rules and other people following the rules. You want to have a safety strategy on that. So, okay, so I think it's a slight flexibility today because we did only 2 lectures and spend more time on this. Maybe I have underestimated how much is needed to code up these things. But I'm pretty sure that actually as we go on, you'll get used to the toolbox, you'll get used to the way what I expect you to code up, and that actually eventually as you start generating some interesting objects, this will become more enjoyable exercise for you and quite helpful for your projects, I hope. So that's all for today. I'll see you tomorrow 9:15, I guess. Sit here. I asked for questions 5 minutes ago, but okay, go on.
It's not a question related to the subject. It's the same thing that I asked today morning.
So slides for today's lecture.
Tomorrow's lecture.
I'll make available. Now, can I check one thing with you? Did you all send me the email addresses? Okay, so those who did send me email addresses, when I get back to my room, I'll definitely do that. I'll send you a link to the slides of lecture 1 and lecture 2. Now, there are parts in the lecture 2 slides which I didn't cover today. We'll cover it tomorrow morning very briefly. And then we'll go to the lecture 3 and
may I ask you to give tomorrow's lecture slides in advance because let's say
okay, I can't for a few things. So for a few reasons. First reason is, as you see today, we kind of changed. I didn't do 2 exercises and 1 lecture, so I don't know how much will be covered. So things might change. So I might decide to drop certain lectures from the slides because I want to cover certain things for sure, and I want to keep some other things outside of that.
the reason I'm asking is that, let's say we both don't have any background in nonlinear.
Okay, so I will send you literature.
Okay, that would be
So there is a list of literature,
Have the literature.
but I'm not so sure if they get it.
Oh, do you have
I don't think they did get it.
then do you have this course online?
Yes, yes.
It should be on Kindle.
So actually I did upload literature on a Google Drive and I think I sent the link, so you should actually download it. And there are a few books and few things that actually you can look up. Yeah. I split it like a books, articles, theses, conference papers and so on and so forth.
so, but it's a lot to read. We can prepare for the lecture tomorrow in advance.
Well, what's the point of you reading what I'm supposed to be telling you tomorrow? If you do that, you'll... So the slides and the papers are there for you to read in your time. And the lecturer is there to give you kind of additional explanations which you won't find in the slides and the papers. So if you read everything, you'll expect me to give you explanations you created for yourself. And my way of thinking about the problems and your way of thinking about the problems may not be the same. So you might not be hearing what I want to be saying, and then actually both of us get disappointed. No, so there will be literature, slides will be given after the lectures, and I'll be adding some of the maybe code with the numbers and the data for you to experiment. I think that's fair. And I really want you to kind of get hands-on experience with this. Even though it might seem painful initially, after a few things you've done and seen the outcomes, it will motivate you to play with the code more. And ultimately, you will have to be coding things on your own. Okay. Well, thank you very much. Thank you.